learners away from the idea that they have to always have the same number of things in their category. And so forcing learners to not rely on those shortcuts and crutches that they've leaned into in the past is a positive thing. The next slide, on slide 3, I don't care if you all do that one, but if you notice that on slide 3, I've then intentionally forced learners to be out of their comfort zone and taken away a lot of the supports to what a parabola would be. What does it mean if D is a positive 25? And it's a sketch, it's not an exact picture, but what would it mean? What would a correct answer here be? And I think that's really important that we give learners that ability to construct math representations that may not have to be perfect. So Rochelle Gutierrez here is actually plotting points and probably calculated. Vihart just drew something that is crosses the x-axis twice. And then we have, you can see it on the overlay. You can see that people are calculating. I'll be honest, when I designed this and what I would think, I would be completely happy if a learner just did that. Because the idea is if D is a positive number, it has to cross the x-axis twice. Even if there was someone here, yep. Nailani Joshi here is doing the calculations, figuring it out for sure, right? And that's great, but that's not the point. The point is just, can you give me something that looks reasonable? There's also some other tools here we can use for questioning. So I'm gonna, not everyone has 2 computer screens, so not everyone may be able to see what I'm looking at on my screen compared to what you're looking at. So I'm gonna hit pause for a second. One of the really effective tools is this little icon up here in the corner, the picture. How many people have used and are aware of the camera icon and what it does? Or actually, if someone wants to tell me if they don't know what it does, because they don't want to spend time on something if everyone knows what the little camera icon does. Okay, perfect. So the camera icon is incredibly powerful for student questioning. Just click it. It says a snapshot was captured. And then we can come over here. This one is pretty approximately correct. And so I clicked it again, snapshot captured. And then I'm going to snapshot this one. So when I'm using Desmos in the classroom, when I find, you know what, let's do this one too. When I find student work, learner work that is particularly interesting for our conversation, I click on the work, snapshot it, and then up here in the top corner, there's the snapshots. It shows I have 4. I can drag the snapshots here, and I can create an album with it. And then I can hit pause, and I can have 2, 3, 4 different things here. And I can actually type a question. So while learners are working, learners are engaging. And now I can show this on the screen and have the learners actually have this conversation. Is this a correct representation? What's wrong with these representations, if anything? Why are these better representations, and why? And of course, as math teachers, we know that we would want to see the little arrows there. Not every learner is going to do that though, but the snapshot feature allows us to pull learner work, show learner work, compare learner work. I can put all these together so that we can have them as one. I can have them separate so that they're two. It just depends upon how we want to have that conversation with the class. So notice the Desmos activity here I've set up allows us to move from individual work to all class work in a couple of different ways. The snapshots being one of them, the overlay feature being another one. And on the overlay, I can show this to the class, and we can say, yeah, you all are fabulous. We do not need to spend any time working on this. What questions do you have so far about just a couple of the little features here that I've introduced, if any? Okay. Nothing in the chat. That's very cool. So let's keep going on our slide deck, and I will unpause. We're going to come to, I asked the question in a couple of different ways. Slide 4 wants a parabola facing down. And then slide 5 shows how I would come back to the card sort and re-engage learners with the card sort so that I'm reinforcing the idea of what I want them to really take away from this exercise. And then slide 6, I want them to actually type it out themselves. I want to see their thinking, their thought, what actually are they engaging with in the lesson. So instead of constantly only setting up the idea for them, the goal is to get that higher level thinking, the comparing and contrasting, the analysis, and really encourage learners to engage in that practice of analysis. So slides 2 through 6 are using a card sort to kind of encourage and help with that analysis. Breaking it up with some sketching is just a good practice because, again, it's about the learner producing their own work. What's also interesting, those snapshots can be used with typed responses as well. So as you give learners the opportunity to type their responses, you can pull up different snapshots of typed responses and have that whole class conversation, comparing and contrasting as well. Which brings up the interesting question, as I was designing this, is, are you all comfortable creating your own activity like this? And so do you want to see the other side of it on how to create this activity so far. Perfect, okay. So I have that also queued up here. So I'm going to hit pause so that we can come back and share my screen again. Awesome. So when you go to when you go to teacher.desmos.com, make sure you create your own account. Very important to create your own account. And then just couple little secret things here. Click on the arrow, click on Desmos Labs, and check all the boxes for yourself. Give yourself all of the tools that are available to you. Also check your account settings and just make sure your name and everything is in there correct, like you want it. But super important, click on Desmos Labs, give yourself all of the tools that are available. The other thing that we're going to do here is we go to custom activities. And I have a whole bunch of custom activities just because I've created them. But click the big blue button here that says create a new activity. And when you do that, it just looks like this big blank screen. And that big blank screen can be a little scary or intimidating. But if you think about it kind of like a PowerPoint, it works really well because there are blocks of things that you enter. So you can do a note, which is just for you to type in. You can ask for a free response for learners to type in, and you've seen a couple of those boxes already. You can require math to be typed, multiple choice, which are exactly what we would think about it. We can ask students to order lists where they have to categorize things from top to bottom. There's also edit, delete. It's incredibly flexible in that sense. You can insert graphs, sketches, media or pictures, geometry. Geometry will not be available to you unless you activate it. Tables, action buttons. So you can add and subtract and create whatever you wish. And then there's some full screen items. So when I looked at mine, the first thing I did is I said, let's enter a card sort. So I grab the card sort, drag it over, let it go. Again, it's blank, but over here it gives me the types. So I b squared, b squared minus 4ac equals. So a text card allows you to type in math by clicking here. You can italicize, bold. You can put an image, just drag and drop from your desktop or from a folder. You can enter a graph. And there's our graph. When you click preview, it'll then show you everything randomized. So creating a card sort is incredibly easy to do. And that's how I created all of the different cards for the card sort. Is just one at a time. I first started with what I thought would be the top cards. And then I just went through, created graphs, created all of the text, and built it like that. If you wish, you can edit an answer key. That way the learners will know on the teacher screen. You can check the answer and you'll see red or green connections on the teacher screen. So that way you know if learners are doing it correctly. This one looks pretty good, or not. So the initial setup for a card sort is really easy. I love card sorts on Desmos because I hate card sorts with paper. I literally detest card sorts with paper because inevitably someone's going to lose a piece of paper or write on it or something. Whereas a card sort on Desmos, I don't have to manage that paper aspect. For the sketch, all I did is grab the sketch, drag it over, create a new slide here, drag the sketch over, customize the background. If I want them to have something to compare against, I can edit the graph. Click done. And so now the sketch will start with that. And then learners can have the sketch however they want to. Just depends upon what you're looking for or whether you're doing geometry, in which case I might have the background blank, or I can actually put a picture in the background and have them sketch it out themselves. Put a picture of cute kitties in there. And so now when the sketch is, you can, and there's lots of reasons to do however you want, all three different options. It just depends upon what your goal is. Same thing, I just deleted some cards and added some cards. And then finally on the comparing, I added a note, type in the note, and then I added a free response. There's some interesting things here. This little checkbox of show students their classmates' responses will randomly pull 3 student responses to show, or it will not show. That depends upon whether or not you, the teacher, want students to learn from the other students and refine their ideas, because they can always go back and edit their ideas, or whether you just want that one shot. I think there's reasons for both. It just depends upon what your individual goals are that day versus a different day. And then I entered this for you all. To do this next piece, let's play around with number 8, slide 8 for a moment, and we'll see what, there's actually some interesting math there, but then I'll show you how to construct something like that as well. So I've unpaused it. If you want to all jump to slide 8, we'll see what happens. Like really think about what's the movement of that black dot. And I'll leave the overlay on because it's interesting on the overlay. And I'll give you a moment to play. All right. And if you jump over to slide 9, slide 9 actually has the answer, because I wanted to make sure that you could see the answer. And Nalini Joshi asked a really interesting question. Is there a way the vertex could create a problem that opens upward? The answer is yes. It's just that the initial parabola that I graphed has to open downward. So I'm going to hit pause again, and I'll show you how I built these slides, because these slides are different and have some very different programming involved in them. What I did to build this slide is I grabbed a graph. And the graph takes up the whole screen. However, if you then add a note, you can add the note and the free response. So now you have the graph and other things, other elements. If you leave them, and you will just have a full graph. And this is the same as selecting full screen down from the bottom. But I have these 3 elements. I'm going to edit the graph. Notice that everything here on the left was hidden from you. It was hidden because you only had part of the graph accessible to you. I just entered the parabola. I left B as a slider, so that way you could move that around. If you create a folder, so hit the plus and create a folder, only in Activity Builder is there a feature to hide this folder from students. And we're going to see I'm going to use that again later in another slide. But what's really interesting is that you can create that point just by entering the values in math of that point. Click on the label, and that'll show you the values of that. We come over here to that slide 9. All I have to do is change this to open down and change my signs, and now that actually will open, the parabola it makes will open up instead of down. It's very curious math that the parabola that's created by the vertex is completely independent. The equation for that is completely independent of B, which is kind of cool. Interesting on math. But that's how you would create slides like this. And then I have a fairly complex one that I wanted to show that I built off of this really bad question from the textbook. So the area of the surface of the swimming pool is 220 square feet. What's the length B of the deep end in feet? So everything's given to us. And my initial thought was, what if we don't have everything given to us? How could we model that in a much more constructive way? So I'm going to unpause. I'll tell you that slide 11 and 12 actually has some extensions of this, and I'll let you kind of play with it a little bit, and then we'll deconstruct how I built this, because this did take a little bit of effort to create. So if you want to jump to slides 11 and 12, you can play with this a little bit. in reading Marcia's question in chat. So Marcia's question is about the computation layer, and I'll show how to access the computation layer here in a second. But I will say, Marcia, yes and no to your question, and I'll get into resources for computation layer here before we leave today. I'll tell you that the answer may not all be exactly what you're looking for, to be honest, because there isn't like a one-stop shop for computation layer. All right, so let's take a dive into how I built this one. Sorry, I apologize, I didn't warn you about pausing. If you haven't played around with Desmos in class and used an activity builder in class, especially if you do a marble slides, just going to tell you, always warn your students, warn those learners before you hit pause, because I have had multiple F-bombs dropped in class when everyone's really focused and engaged in an activity and I just hit pause without warning them. And it always made me happy when kids are like, what the bleep, Waddell, what are you doing? Right? Because that means they were really involved and engaged. That's kind of funny. So this required actually some setup, but what's really interesting is if you're comfortable with the math, all we're doing is just math. For the learners, I turned off the X and Y axis because I wanted it to be blank, but for creating, I absolutely would have the X and Y axis on. I also locked the viewport so that we couldn't move it around, and so only one thing could move. So there's some additional features here in the activity builder that aren't in the regular Desmos calculator. I also did something funky here, and that's I used lists. So the square bracket, -5, (5) is a list that all at once creates the top and bottom. So if I wanted to do multiple lines, I could use 3 dots, and that would give me a list from -5 to 5. If you use a comma, you're just going to get the 2 lists. So using the list is a really fast way to draw multiple lines. And then I used a domain and a range restriction for the blocks. You can label lines with the points. If you just click label, it'll say the value. If you type in text, it'll give you the text, so that you have that freedom to use either the math or a number or the word. The other thing you can do is right here, and it's probably really hard to see, but this is the tilde button right next to the one on your keyboard has a backwards apostrophe. This is a backwards apostrophe, $, and then the letter F, because the letter F I defined, where did I find F? I defined it right here. So $, wiggly bracket F allows me to pull the value here. So that's how I can get 11.5. I didn't give you 11.5. I turned off the label, but I was arguing with myself at one point whether or not I wanted numbers or, oh no, sorry. First slide was number, second slide was another word. But so the labels, you can actually put variables into your label and have the labels change. But it's just going through to construct something like this and just putting in the math step by step. I can put it all in a folder and click hide. So I could actually put this entire screen into and let learners actually play with it and do math here on the left. I didn't want to do that, but by putting it in the folder, I was able to just really quickly and easily hide it or reduce and minimize. That's actually the same way I did. And then, because this was complex, I didn't want to redo everything for slide 12. I used the triple dots over here and I just duplicated. So you do something fairly complex for one screen, you don't have to completely redo it. Just duplicate it and edit. A lot like we do for PowerPoints and material that way. What questions do you have? Not computation layer questions, we will do that in a second. What questions do you have about creating your own activity builder and developing your own activities? So let me show you one more technique and tip for building your own activities. There's a lot of activities out here. So if I type in Desmos activity builder, and let's say I want, and that's exactly, Pinky's asking the question to them. I'm going to show you. Let's do linear functions. And wow, this one looks really big. And it was created by Jennifer Williams. So linear functions, there's some self-checking. That's important for computation layer. So I'm definitely going to plus this and add it to my collections. Oh, I don't have a collection yet for computation layer. So I'm going to do that. Create new collection. Great. So now I have this collection called computation layer. There is, and I'll show you that as well, Vivian, before we're all done here, because we've only got about 10 minutes. So we're going to wrap up on a strong note of here's how to find and build, or how to find and kind of make it much easier. So I've added this to my collection so I can find it later. Collections are found over here on the left. So here's my collections, but there you go. Sorry. But I'm going to hit the triple dot this time. Instead of the plus, I'm going to hit the triple dots and I'm going to copy and edit. The copy and edit allows us to do exactly what Pinky asked. So I'm going to copy and edit. And this is now in my collection, and not my collections, but my custom activities. Notice the title says copy of. And forever now, as I edit and change, this will say created by Jennifer Williams, edited by Glenn Waddell. So that way the record and the record of who created it and who edited it will always be there. And now I can go through, because maybe in your class you're using, let's see if there's some language here that we don't want to use the word correct. We want to use a different word. We want to say yes. The word yes will appear when your answer is right. So you can go through the entire slide deck of the activity, edit, change language, change however you want. However, the computation layer is how the word correct will occur in here. And if you see up here, this is named slope 2. That matters because this is the computation layer. No, Amelia, you can create and keep it private. So I'm going to click on this little bar here. And here's documentation. And the blank space here is the computation layer. So I'm going to, and you can see how this is white, but this over here is teal. Here's actually all of the computation layer code to put in the word correct when they figure out the slope is correct. It's all it takes is those 2 lines. But what this means is, and this is important for Marcia's question. So Marcia Googled and found the computation layer documentation. This is the best place to find, and it's just teacher.desmos.com, computation layer documentation. This is the best place to find the resources that Desmos has created for computation layer. However, one of the easiest ways to really understand is to find a computation layer, find a activity that does what you want it to do, and kind of go through and play. Hopefully the person will follow good practice and document their code. There's some components over here that will help explain. And just look for these little elements here as you go through. You can see how not every slide here has a computation layer, but some do. Some of the coding is fairly small, and some of the coding is larger and more precise. But you can go through and edit everything that anyone has done. So you absolutely do not have to build from scratch. You can find those activities that are really solid, really interesting, really good. Take them into your own account and edit them to your heart's delight. And that gives us, like, I know we're done at 1:40, so we have just a couple minutes. What else can I help with? What else can I show? Yeah, Marcia, I think that's really important. Don't think you have to code from scratch. There's a whole bunch of self-checking activities that other people are making. Find them, find an activity that you really like, and you can just edit that activity and make it your own without needing to do it on your own. So there's 2 different ways to search for activities, Carrie. The first way is with this search button up here, or search box up here. So I'll search for linear functions. The problem with the search box on Desmos's website is this search box will only search Desmos activities. So these are curated, incredibly high quality. If you wish to search and find activities that anyone else has made, just do a Google search and include the word activity builder or Google Classroom in your Google search. And you'll find many, many activities that other teachers have made. And Ivan Chang, all you need to do is hit the triple dots, copy and edit, and it's yours. Yeah, I oftentimes will search for teachers' activities, find one that does what I want it to do, and then improve it, give it my own spin, and not try to not try to create it myself, because it's far too much effort to create it yourself. What other questions? I'm not sure about Nearpod. I haven't used Nearpod, so I don't know. I'm sorry for not knowing that, but Nearpod is not something I have a lot of experience with. That runs us up into 1:40. It's such a fast conference. I hope all of you are enjoying and finding things that you can use here. And if you ever have any questions, please feel free to reach out. I'm more than happy to help.
Thank you very much, Glenn. We appreciate that you introduced us to the world of Desmos and a lot of activities and functionalities that has been exposed to us. And we would like to thank you for sharing this information with us. I'm posting the attendance and survey for this session, and if you'd like to get a certificate of participation for your CE units or hours, please click the link at the chat.
Awesome. And I just put my email and Twitter.
Sure. Yeah, please.
I have a Mastodon too, but I don't know off the top of my head what that address is yet, just in case Twitter disappears soon.
Okay.
But please feel free to reach out. I'm more than happy to help anytime.
Mr. Mike, I could not see the survey link.
Okay, let me post it again.
Thank you.
So the survey link is together with the attendance link. So the one below is the survey link.
It's not going into the chat.
Not? Okay, I'm sorry. Let me post it again. Let me post it again. Okay.
There it goes.
There we go. How about that? Okay.
What room is this?
So I'd like to have this opportunity to. Okay. Room 2. This is room 2, session 4. I'd like to acknowledge the presence of our next speaker, Bill Hanlon. So if you're gonna stick around, we're gonna start in 3 minutes for our next session with Bill Hanlon. Bill Hanlon will be talking about linking elementary and secondary topics. So Bill Hanlon, for everyone to know, he is the former director of the Southern Nevada Regional Professional Development Program, or SNRPDP. He's noted speaker, author, educator, consultant, and coach for schools, and international speaker, national presenter for organizations such as AASA, ASCD, ALAS, NMSA, NASSP, NSBA, and NCTM. Bill was also the coordinator of Clark County School District's Math and Science Institute, and was also responsible for K-12 math audits. He served on the Nevada State Board of Education, Regional Director of National Association of State Boards of Education, and as a member of National Council for Accreditation of Teacher Education, NCATE. State Partnership Education, NASB, and its member, National Council for Accreditation of Teachers. He also hosted a television series, Algebra, You Can Do It, on PBS Las Vegas. Bill's book, Building Success on Success and Teaching Struggling Students in Math, can be purchased through Rowan and Littlefield. I'm assuming it should be on Amazon too. So, ladies and gentlemen, I'd like to welcome Bill Hanlon for the next session.
Okay, thank you. Okay, Mike, what time are we getting done? Just so I know for sure. Mike, what time do we get done? Can you hear me okay, Mike?
Yep.
Okay.
We're gonna get done at 2:40.
Okay, so we're starting right now, is that right?
That's correct.
Okay, good deal. All right, so today what we're going to do is looking at how we can connect what's being taught in elementary school to what's being taught in secondary school. I would tell you the biggest difference between elementary school, the math taught in high school, and particularly in algebra, is mostly vocabulary and notation. So what my intention is to kind of walk you through a number of examples for two reasons. One is if in fact you're a elementary school teacher, you need to know the stuff that you're teaching is going to impact what students will learn later. And for secondary teachers, it's important for you to know how to link what they're teaching to what you're currently teaching, because the whole idea is that we make students more comfortable in their knowledge and their understanding of math. And the way we do that, to be quite frank, is through linkages and through using, and this is the important part, using simple, straightforward examples that work, that clarify what you want them to learn, and then don't bog them down in needless arithmetic. So let's go ahead and get started. Now, if I go off the page or you don't understand something, please, or if I make an arithmetic mistake, please jump in right away. Don't let me just continue to babble on if I said something like 4 + 3 is 12. Okay, so in elementary school, we have problems like this, 432, and we ask the students to write that in expanded notation. So that's 4 times 100 plus 3 times 10 plus 2 ones. In an elementary school, we call that expanded notation. Later, what we do is we show them how to write that without the X for times, and rewrite that as 4 times 100 plus 3 times 10 plus 2 times 1. Then, of course, they learn about exponentials. So they learn to write this as 4 times 10 squared plus 3 times 10 plus 2 times 1. And then we might say to them, let's let n equal 10. And we rewrite this as 4 times n squared plus 3 times n plus 2 times 1, I'm going to call 2. And then we get to a class like algebra, and we say we're not going to use the dot anymore, and we like to use x's. So we're going to rewrite this as 4x squared plus 3x plus 2. The greatest thing that changed here is the vocabulary and notation. We started off in elementary school as 4 times 100 plus 3 times 10 plus 2 times 1. We changed the multiplication sign to a dot. Then we can change, we said let n equal 10, so we use substitution. And then all of a sudden, instead of saying 4 times x squared, we're saying 4x squared plus 3x plus 2. And we're using exactly the same concept that we use up here, except up here it's called expanded notation. In an algebra class, of course, this is called a polynomial. All right, now I can't make math any more difficult, but with little kids, if the kids understand place value and we have a problem like 341 plus 256, what we have the kids do is they say we have 3 plus 2 100s. We have 4 plus 5 10s. And then we have 6 plus 1 ones, which turns out to be 500s plus 9 10s plus 7. And if we multiply that out or add that together, that becomes 597. Well, what does that look like when they get to an algebra class? 341 looks like 3x squared plus 4x plus 1. And we're going to add that to 256. In an algebra class, that looks like 2x squared plus 5x plus 6. In elementary school, we tell kids add the hundreds to the hundreds, the tens to the tens, and the ones to the ones. Now what we're going to do is we're going to combine what we call like terms, which means we're going to add the x squares to the x squares. We're going to add the x's to the x's. So just like up here, I'm going to take my x squares and I'm going to have 3 plus 2 x squares plus 4 plus 5 x's plus 6 plus 1, which is 7. And when I rewrite that, that's going to become 5x squared plus 9x plus 7. Notice down here, in elementary school, I'm adding hundreds to hundreds, tens to tens, ones to ones. Down here, I'm adding x squares to x squares, x's to x's, and numbers to numbers, except we don't say that. What we tell kids is combine like terms. My point is this, just like with expanded notation and polynomials, the biggest difference is the vocabulary and the notation, how we say it and how we write it. Combine like terms actually means add the hundreds to the hundreds, tens to the tens, ones to the ones. And so the math itself doesn't change. If I want to teach multiplication of binomials, if I have a problem like 32 times 21 that's taught in elementary school, we go with expanded notation. 1 times 32 is 32, 2 times 32 is 64. We draw a line and add and get 672. In algebra, what does that look like? 32 is 3 tens plus 2 ones. I'm just going to rewrite that as 3x plus 2. The 21 is 2x plus 1. And as I multiplied 1 times 32, I'm going to multiply 1 times 3x plus 2 and get 3x plus 2. Notice the partial product. Here are the digits of 32. Here the coefficients are 3 and 2. I indent a space and multiply, so I get my 6x squared plus 4x. And notice here's my 6 and 4 for my partial product. Here's my 6 and 4 for my partial product. I draw my line and add, I get 6x squared plus 7x plus 2. So the point I want to make is the algorithm, a standard algorithm that's taught in elementary school, is also going to be used to introduce multiplying with polynomials. Then what we do in algebra is we have a tendency to look at that horizontally. So I'm going to write this as 2x plus 1 times the 3x plus 2. And the way we do that is we multiply the 2x times both of those numbers, then we multiply the 1 times both of those numbers. So 2x times 3x is my 6x squared, 2x times 2 is 4x. And you can see that was my partial product that I had before. Then I multiply by 1, 1 times 3x is 3x, 1 times 2, is 2. And then I combine like terms, I get my 6x squared plus 7x plus 2. So these algorithms that we teach in algebra come directly from the elementary standards that we do in the math. Okay, let me just say this, if I got some chats here. Okay, all right. I'm blind, so if you write something and I don't respond to it, yell at me. Okay, so let's go ahead. So now the point that let me get back over here because I can't find the damn thing. All right. And there I am. Okay, so the point I want to make is this. The math that you teach, particularly in algebra and geometry, is math that has already been taught. You need to understand that. From an elementary perspective, you need to know what you're teaching. Those teachers rely on to be able to use it. So, in elementary school, as you learn how to do prime factorization and all that kind of good stuff. Is that important? The answer is yes. Let me show you why. In high school, if I want to factor a polynomial like x squared plus 19x plus 48. Okay, Well, what a lot of teachers do, I don't know why, except that they don't want to drive kids crazy. They make a big X over here and they do a lot of crap. Okay, so what I'm going to suggest to you is when you have a constant like 48, you come off to the side, write down 48. And now what we're going to do is use division by primes and the multiplicative inverse. So I'm going to write 48 as a product, 48 times 1. I'm going to divide that by 2 and have that 24 times 2. So if I divide this by 2 and multiply by 2, that's the multiplicative inverse, which means I'm multiplying by 1. If I divide this by 2 and multiply that by 2, notice I still get 48. If I divide this by 2 and multiply this by 2, I still get 48. If I divide this by 2, multiply this by 2, come on, Hamlin, you can do that. That's a 16. All right, then these are, and I can't divide by 2 anymore. Okay, so if I ran out of factors, what I could do is I could start dividing this by 3, the next prime number. Now, in terms of algebra, if you write down all those factors, you say which ones of these add up to 19. That adds up to 49, 26, 16, 16, and there we go. 3 plus 16 is 19. So this is the factor of x plus 3 times x plus 16. So using prime factorization and factorization helps you get that. Now, how do I know if I have all the factors? Well, let's do our prime factorization. 48 is 6 times 8. 6 is 3 times 2, and 8 is 2 times 2 times 2. To know if I have all the factors, I rewrite this as 2 to the 4th times 3 to the 1st. All right. And in terms of doing that, I have, if I add 1 to each of these exponents, so the exponent here is 4, I add 1, I get 5. This exponent is 1, I add 2, I add 1 and get 2. If I multiply 5 times 2, that will tell me how many factors there are in the number 48. So you can see I'm going to say 5 times 2 is 10. And let's see if I have them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, from elementary school, learning how to do prime factorization and dividing by primes, I can find out all the factors. And if I'm not sure I got them all, what I can do is use prime factorization, add 1 to each exponent and find that product. And that should tell me how many factors I have. So let me just give a different one. So I have to divide out by another number. Let's say I have a problem like x squared plus 23x plus 60. Okay, now I know some of you can factor that very quickly in your head, but the way we do that, if you're looking for a systematic approach to finding the factors, that's 60 times 1, divide by 2, which is 30 times 2, divide by 2, which is 15 times 4. I can't divide by 2 anymore, so what I'm going to do is my next prime number is 3. Divide 60 by 3 is 20. And what did I just do? And multiply by 3 is 23. So, whoops, there I am. So there's my factors. Now, is that all the factors? The answer is no, because if I took 60 and rewrote that as 10 times 6, this is 2 times 5 times 2 times 3. So the factors are 2 squared times 3 times 5. If I add 1 to each exponent, that's 3. This is 2. This is 2. So we'd know there's 3 times 2 is 6 times 2. We'd know there's 12 factors in 60. I only got to 8 of them because I'm going to stop right there. Okay, now, once I get to this, I can go ahead and start now dividing by 2 again, get 10 times 6, and then divide by 2, 5 times 12. So I divide, multiply by using the multiplicative inverse. The point that I want to make is little things like prime factorization that you do in elementary school is going to affect how you do factorization, polynomial factoring in high school. The nice thing about math is it's so connected. I'm trying to go fast here, so if I'm going too fast and you need me to slow down, just yell at me. Okay, let's have you all add fractions in your head, but also not only adding fractions in your head, let's see how you can do that using rational expressions. Oftentimes, when I'm talking to secondary math teachers, they say things like, how the hell can I teach kids how to add rational expressions? They can't even add fractions. Okay, I got it. But if you use linkages, you can go back and review and reinforce and address any deficiencies they have. So let's start what they do in third grade. Let's say, I'm going to start off with unit fractions, because I always start off with simple, straightforward examples that work, that clarify, that kids go, oh God, got it, that was too damn easy, and then I scaffold. So let's say I have a problem like 1/3 plus 1/2. In little kids school, 1/3 looks like this up here. 1/2 looks like this. I can't add those together because the definition of a fraction is it's part of a unit made up of two parts, the numerator and denominator, and the denominator tells you how many equally sized pieces, how many equal parts make one whole. These are not equally sized pieces, so I can't add them together. So what I'm going to do is I'm going to take this cut and put it up here. I'm going to take these two cuts and put it down here. And now when somebody says, how many pieces do I have? Now you can say I have 2 out of 6. And here you can see I have 3 out of 6. And if I say, well, how many pieces do I have altogether? I can count 1, 2, 3, 4, 5. I have 5 pieces altogether. And how many pieces make one whole unit? That's 6. So when some kids want to add 6 and 6 and get 12, besides slapping them upside of the head and say, you can't do that, the reason you can't do it is definition. The definition is the denominator tells you how many equally sized pieces make one unit, not 2. Okay, so let's say I did 2 or 3 of these problems. After I did 2 or 3 of these, what I would do is introduce math speak. So here we made equally sized pieces and we renamed it, and then we counted how many pieces we had. But what we do is after we do a few of those, we develop an algorithm. We tell kids to add or subtract fractions. What do? You find a common denominator. Second, you make equal fractions. Third, you add or subtract, come on, Hanlon, the numerators. Fourth, you bring down the denominator. So what you do is you build an algorithm so the kids are acquiring the language that's important to math. And I have to tell you, what causes kids difficulty in math has nothing to do with math. It has everything to do with not knowing vocabulary and notation. So let me get off this for a minute and just give you an example of that. If I gave you this here, 8x squared y cubed z to the 5th, and if I ask the average student, what is the degree of that monomial, I would get a bunch of blank stares. But as you know, to find a degree, all you do is add the exponents. 2 plus 3 is 5, plus 5 is 10. The degree is 10. My point is this. If kids couldn't do that problem, it has nothing to do with the math. It has everything with not acquiring the language. Okay, back to the fractions. We said would find a common denominator, make equivalent fractions, add, subtract the numerator, bring down the denominator, and simplify. Well, that works out fine if I have problems like this. 3/5 plus 1/4. No, I can find the common denominator pretty easily by multiplying. I can make equivalent fractions. 5 times 4 is 20. So 4 times 3 is 12. 4 times 5, that's 5. So I get my 17/20. So adding fractions, piece of cake. But now what happens is this. What if I have 5/18 plus 7/24? What do we tell kids to do? I swear to God, what we tell people to do, we tell them to multiply. Are you kidding me? We're going to multiply 18 times 24 and come back to this problem this week. The next way we tell people to do it is to write multiples. What kids are you teaching? What kid do you know can write, goes 18, 36, 54, 72, 90? Hell, they can't skip counting tens, never mind 18. Skip counting is how you're going to find a common denominator? I don't think so. Do you hate kids? Are you going to make them do it the least common multiple? Are you serious? That's how you're going to find a common denominator? Hell no. What you're going to do is you're going to show them the reducing method. Now, what the reducing method comes from the least common multiple. But in the reducing method, all you do is you put the two denominators over each other, either 18 over 24 or 24 over 18. I don't care which it is. You reduce. Well, now you call it simplifying, but that screws up my jokes. So I'm going to simplify this. This reduces to, it simplifies to 3/4. When I cross multiply, 3 times 24, 3 times 20 is 60, 3 times 4 is 12, 60 and 12 is 72. My common denominator is going to be 72. And as you know, 4 times 18, 4 times 10 is 40, 4 times 8 is 32, 40 and 32 still gives me 72. Now, what's nice about using the reducing method, when I say 18 times what gives me 72? Whoops, there it is. It's right there. It's 4. So 4 times 5 is 20. If I say 24 times what gives me 72, it's right there when I cross multiply 3. So 3 times 7 is 21. So bottom line is, if you understand the at least common multiple, you can find the common denominator by simplifying. Now, let me get back to the fractions. We said a minute ago, 1/3 plus 1/2. We said that answer was 5/6. If I was working with kids, I would give them some more problems like 1/4 plus 1/5. We would find out that answer is 9/20. And if I had a problem like 1/4 plus 1/3, that answer is 7/12. After I drew these pictures and had the kids add those, I would ask them, can you look at this problem and tell me where the 6 came from? Can you look at this problem and tell me where the 20 came from? Could you look at this problem and tell me where the 12 came from? And most kids would say, yeah, I get it. Now I could say to them, well, look at the same problem. Can you tell me just by looking where that 5 came from? Can you tell me just by looking where that 9 came from? Can you tell me just by looking where this 7 came from? And most kids are going to go, oh, dang, why am I doing it the long way? Because now if I said to them, what is 1/10 plus 1/3? What they're going to describe is to get the denominator, they're going to multiply. To get the numerator, they're going to add. And the answer is 13/30. And of course, when you do a problem like that in math, you always typically end it with a POC. Okay, everyone knows what POC stands for in math. This is very important notation. Okay, it stands for piece of cake. There you go. Now, after I do a bunch of those with unit fractions, what I'm going to do is instead of having unit fractions, I'm going to throw different numbers in there. So let's say I have a problem like 3/4 plus 1/5. I know my common denominator is going to be 20. My numerator is going to be 19. If I had a problem like, let's say 1/10 plus 3/7, my common denominator is going to be 70. And my numerator is going to be 37. If I have a problem like 2/5 plus 1/3, my common denominator is going to be 15, and my numerator is going to be 11. So now I'm going to ask kids, do you see where the 20 came from? Do you see where the 70 came from? Do you see where the 15 came from? And again, most kids are going to do that. Now, when I ask them, where did this 19 come from? This doesn't jump out at you. Where does this 37 come from? So what I'm going to ask kids to do is you can't stand there and stare at this sucker. You got to play these games. You have to multiply, move stuff around. So is there any way I can get a 19 by combining these numbers somehow? Is there any way I can get a 37 by somehow combining those numbers? Is there any way I can get 11? And if I had more time, we would let the kids find that. And what you start to realize is if I multiply 1 times 7, that's 7. 10 times 3 is 30. Oh my God, that gives me 37. Same thing down here. If I multiply diagonally, 3 times 5 is 15. 4 times 1 is 4. I get 19. Unbelievable how this all works out. Same thing here. 5 times 3 is 15. 2 times 3 is 6. 5 times 1 is 5. 6 and 5, sure enough, gives me 11. So now if somebody says to me, what is 3/4 plus 1/7? I know my common denominator is 28, and then I'm going to multiply diagonally. 3 times 7 is 21. 4 times 1 is 4. 21 and 4 is 25. So what we do is we generalize that now. What if I have algebra like 2 over x plus 3 over y? Well, my common denominator is x times y. My numerator is 2y's plus 3x's. Okay. Now, what's nice about math is you can never make it harder. You can only make it longer. So let's say I have a problem like 2 over x minus 1 plus 3 over x plus 2. My common denominator is going to be x minus 1, x plus 2. My numerator is going to be 2 times x plus 2 plus 3 times x minus 1. Okay, when you get done with those problems, you normally make a little happy face. And if you want, you can put eyebrows with it. There's the little nose. But anyway, you look at this stuff and you think, okay, what have we done? You know, if I talk to a lot of teachers teaching algebra, they're thinking, I'm supposed to add rational expressions. The kids can't add fractions. If you link it and you use simple, straightforward examples that work, So what we did, like with this fraction stuff, we looked at drawing pictures to add them. Then we changed that to math speak. We build a math algorithm so the kids are acquiring the language. Then what we did is we went from unit fractions, we scaffolded to not unit fractions. And then we scaffold again to, oh my God, algebra. And, and then here's the nice thing about this. If you do it and if you develop it, now when the kids see something like this, because in a lot of algebra books, this is what you get. You get A over B plus C over D is equal to AD plus BC all over BD. Kids look at this and go, what the hell are you talking about? But if you showed them where that came from, then they'll be able to add those fractions or rational expressions very quickly. So here's my point is, if your book used A over B plus C over D and the kids memorized AD plus BC over BD without understanding, what would happen if they had R over S plus T over V? If they saw it develop, they'd know that SV is the common denominator, and that would be RV plus ST. So if they see it, then the variables that you use makes no difference. Okay. Do me a favor, because I know I'm going like a bat out of hell here because I don't have a whole lot of time. So if you're okay up to this point, put down okay in your chat. If you're not okay, put down an N. So you need to see an okay or an N. Okay, there's 55 of you, so I'm going to use this idea of one-to-one correspondence. There should be 55 okays or with N's. Okay, everyone is okay with that. Everyone's lying to me. Nobody ever wants to talk to me. Okay, why do math teachers talk to themselves? Come on, people. It's because they think somebody's listening. I don't want to explain these things to you. Okay, you're walking down a hallway. You see some kid with snot hanging out of his nose or something, and you say to one of your colleagues, oh, wow, that kid is 288. What does it mean if you call somebody 288? Come on, people, this is math. You need to know this stuff. Okay, if you have 12 of something, what's that called? A dozen. Thank you. I'll talk to myself. If you have 12 dozen, that's 144, right? So what happens if you have 288?
Too gross.
It's too gross. Okay, for those of you who don't know math jokes, you need to go to my website under math and look under humor so you can get some of these. How the hell can you have a party at your home if you don't know math jokes? My God. All right, so let's go back to elementary school. In little kids' school, how many, do I have any element? Do me a favor. A lot of you are not on screen. You got names here. So I can't read, I can't read your body language. It's a good thing I'm not, I teach the RPDP classes. If you're somewhere up north and you're not taking them, then go to the Southern Nevada RPDP website and sign up for the damn things. They're free. They're used for CUs. And if nothing else, you'll be entertained. All right, where am I at now? So bottom line is this. We teach equations. This is what equations look like when in second and third and fourth grade. You have 2 times, and then they have a circle, plus 3 equals 13. And then the kids have to guess what number goes in the circle. So they try 1, and then they try 2, then they try 3. They finally get to 5, and they put the little 5 up there, and now they're happy as it can be. Well, what does this problem look like as the kids get into junior high in algebra? 2 times the circle, which is what they put number in, now looks like this. 2x plus 3 equals 13. So this is how they're solving equations in primary grades, intermediate grades, and this is what it looks like in high school. Well, and how do we get these? Well, somebody has a problem like this, 2 times 5 plus 3. They use the order of operations, which is nothing more than agreement, kind of like driving on the right-hand side of the road is kind of an agreement, unless you want to meet new friends. If you watch a ball game and it says, Boston 5, LA 2, and if I say, where is the game being played? Well, the agreement is the home team is always listed second, so we know the game is being played in LA. So when we have a problem like this, a reasonable person could look at 2 times, let me write it this way. 4 plus 6 times 2. A reasonable person could look at this and say 4 plus 6 is 10 times 2 is 20. Another reasonable person could say 6 times 2 is 12 plus 4 and get 16. The problem with that is we have one problem with 2 different answers. In arithmetic and computation, we don't allow that to happen. The closure property guarantees one and only one answer. So we have to come up with a way so everyone does this the same way. And that's called the order of operations. So we use that. Please excuse my dear Aunt Sally business. Or we say, what the hell's the other one called? God, I forgot what it's called. PEMDAS. Yeah, it spells PEMDAS. That's what it says. Okay, but anyway, here's the way you get this expression. So what we're going to do now is we will do anything that has parentheses. We don't have any exponentials. We have a multiply, so we do that. 6 times 2 is 12, plus 4 is 16. So now we're going to agree that this is the answer. Now, if I gave you directions to my home and you wanted to use those same directions to go back to your house, you'd use the directions I gave you and go in reverse, doing just the opposite. Or I could, let's say I gave you a present. If I gave you a present, I'd take the present, put it in a box, put a cover on the box, put paper on, put tape on, put a bow on. Okay, what would you do to get the present out? Take the bow off, take the tape off, take the paper off, take the cover off, and take the present out. In other words, you would go in reverse, undoing what we have done. So, and if we're going to undo an expression in math, we call that solving an equation. So a problem like this, if I get back over here, if I want to be able to solve an equation, what I have to do is I'm going to have to take the order of operations in reverse using the inverse operation. So if I have this problem here that we just did in little kid school, and we wrote that as 2x plus 3 equals 13. Well, when kids are doing this, 2 times what number plus 3 equals 13, when they're doing that in elementary school, the answers always come out to be nice whole numbers. So they're going to be like 2, 3, 5, there's going to be nice numbers. As you get into later grades, we could get fractions and decimals and all kinds of other stuff. So guessing would not be a great way of doing that, trial and error. So we come up with a systematic approach. And what is a systematic approach? Is equations in the AX plus B equals C format. So AX plus B equals C format. When you have equations that are in that format, we use the order of operations in reverse. So we have a problem like the 2x plus 3 equals 13. What I'm going to do is, using the order of operations, which is the please excuse my dear Aunt Sally, going in reverse, I'm going to get rid of any addition or subtraction. So here's my problem, 2x plus 3 equals 13. How do I get rid of, I have an addition, how do I get rid of it? I subtract 3 from both sides. So now I have 2x plus 0 equals 10. Now, 2x plus 0 is 2x. That's just by identity. So 2x equals 10. I don't have any other addition or subtraction. So I have a multiplication. How do I get rid of that? The opposite. I divide by 2. So x is equal to 5. So what we do is we take what the kids have learned, like problems like 4x minus 2 equals 18. And we use the order of operations in reverse. So we get rid of any addition or subtraction, then we get rid of any multiplication, division, then we get rid of any exponentials and parentheses. So I look at this, and this is in the AX plus B equals C format. So I look at this and I say, I have to get rid of any addition or subtraction. I have a subtraction of 2, so I'm going to add 2 to both sides. So I get 4x equals 20. I now look at this and I have a multiplication. How do I get rid of a multiplication? I do the opposite, divide by 4, divide by 4. So x equals 5. Now, the nice thing about math is you can never make math more difficult. All you can do is make it longer. So if I have a problem like this, ax minus 3 equals 6x plus 9. What I ask the students is this in ax plus b equals C format? So the first thing I'm going to ask students to do is identify what is different about this problem. That has nothing to do with their math ability. It has to do with, can they tell what's different? Well, here I have a number in front of an x plus a 3 equals, well, what I have here is an extra thing here. So what do I have kids do? I have them identify it. Now, once you identify what's different in a problem that is not in the AX plus B equals, the hell is going on here? Why isn't that thing changing? Mike, make sure you tell me what time it is if you don't mind. Don't let me keep going. Once you realize the problem is not in the AX plus B equals C format, what you do is you do what I call using the get rid of it strategy. If you have a problem that has a radical in it, how do you solve it? You get rid of the radical. If you have absolute values, what do? You get rid of the absolute values. If you have systems of equations, if you have two equations, two unknowns, what do? You get rid of an equation. So in math, we use the get rid of it strategy. And the get rid of it strategy is everything comes back to AX plus B equals C. If you have a logarithmic equation, what do? You get rid of the logarithms. If you have an exponential equation, what do? You get rid of the exponents. You get rid of the exponentials, excuse me. So if you have a quadratic equation, what do? You end up rewriting that as a factored form, AX plus B equals C, but now you're going to have C equal to 0. So anytime you're solving equations in math, if you're not teaching the AX plus B equals C format, start today. Okay, having said that now, what you do is you have the students look at a problem they don't know how to do and say, what's bothering you? They identify what's bothering them and you get rid of it. Now, the trick is you get rid of it by using the properties of real numbers, not an eraser. That's the trick. Now, once you have identified what's bothering you, you get rid of it. So you look at a problem like this. If I can get back on there. Yes, I can. I have that 6x over there, which is not an AX plus B equals C format. So I'm going to subtract 6x from both sides. So in terms of subtracting 6x from both sides, 8x minus 6x is 2x minus 3. The 6x minus 6x disappears, and that's equal to 9. And then lo and behold, I have a problem in the AX plus B equals C format. So now I use the order of operations in reverse. How do I get rid of a minus 3? I add 3 to both sides, so 2x is equal to 12. How do I get rid of a multiplication? I divide, so x equals 6. Again, piece of cake. I can't make math more difficult. All I can do is make the problems longer. Now, when you're teaching, notice the numbers that I'm using, how they all came out nice. When you are teaching, if you're using simple, straightforward examples that work, this is what kids should be doing. Got it, got it, got it. Don't be putting stupid numbers in the damn problem where the kids off to the side doing arithmetic and concentrating on something like that, as opposed to learning the concept of skill you're trying to teach. That's important. And that can't happen unless you pick your simple, straightforward examples that work. Okay, so I don't care what you're teaching. It always comes back to AX plus B equals C in terms of equations. And if you think about it, it just makes it a whole lot nicer. Okay. Again, a point that I want to make is the biggest difference between elementary school and secondary schools is the vocabulary and notation. We teach kids, how do you add fractions? You find a common denominator, you make equivalent fractions, you add or subtract the numerators, you bring down the denominator, and you simplify. Well, then how do you add decimals? Well, decimals are fractions. So how do you add decimals? You find a common denominator, you make equivalent fractions, you add or subtract the numerators and bring down the denominator. Except we don't say it that way. What do we say? We tell the kids when you're adding decimals, line up the decimal points and fill in the zeros. Why? Because you found a common denominator and made equivalent fractions. Then you add the numbers. That's adding numerators. But you bring the decimal point straight down, you're bringing down the denominator. So the point I want to make is, as the kids progress through math, the biggest changes are the vocabulary and notation. The concepts and skills stay the same. The verbiage changes clearly. And because in algebra, we're able to see patterns a lot quicker. So a minute ago, when we learned how to multiply binomials horizontally, I think we had a problem. I can't remember what we had. We had a problem like 2x plus 1 times 3x plus 2. And we said you multiply the 2x times both of these numbers and the 1 times both of these numbers. Well, now if I have a problem like 104 times 103, what will happen is you see a pattern. 104 is 100 plus 4 times 100 plus 3. 100 times 100, that's going to have 4 zeros, so that's 10,000. I'm going to have 300s plus 400s, that's 700s. And I'm going to have 3 times 4, which is 12. So 100 times 100 is 10,000. 100 times 3 is 300. 4 times 100 is 400. 4 times 3 is 12. So 104 times 103 is 10,712. So if I gave you a problem like this, what's 102 times 106? If you saw a few of these develop, you know 100 times 100 is going to be 10,000. I'm going to have 2 plus 6 hundreds, that's 8 hundreds, and 2 times 6 ones, or 12 ones. So that answer is 10,812. Now I can hear you right now. You're saying, hell, I want to do one. So go ahead and do 104 times 105 in your head. It's going to be 10,000. You add the 5 and the 4, 900, and then 5 times 4 is 20. So this answer is 10,920. Okay. Again, the nice thing about math, it is so connected. You know, how many of you teach FOIL? All of you, good. So you have a problem like 32 times 21. Whoops, except you can't see it. Please tell me that, could you see what I was doing multiplying by hundreds? Was I on the right screen? Thank God.
Yes.
Okay, if I don't, let me know. Whew, it scared me to death there. So multiplying by FOIL, 2 times 3 is 6. The first, first, outer, inner, last. So the first times the first, 2 times 3. The last, 1 times 2 is 2. The ooey is like the stuff inside a Twinkie. You start to eat the Twinkie and the stuff gets on your fingers and you go ooey. Okay, that's the outers. There's 3. There's the inners. That's 4. 3 plus 4 is 7. The answer is 672. So that, the nice thing about algebra is patterns jump out at you. So if I wanted to multiply crap like this, I could do it mentally. And hopefully what you're doing is when you're teaching, you're using mental math. Now, in a high school algebra class, you teach something called an arithmetic sequence. And you define an arithmetic sequence as a sequence in which every term after the first is obtained by adding a common difference called D. And whoops, here's the formula. A sub n equals a sub 1 plus n minus 1 times d. Now let's go find the nth term of an arithmetic sequence. Can you imagine being a 13, 14-year-old and having your teacher drop that on you? Are you kidding me? Okay, we call it an arithmetic sequence. Now it's spelled the same way you spell arithmetic, but don't call it an arithmetic sequence. It's an arithmetic sequence. It's kind of like you don't have a photographer come to your house, you have a photographer come to your house. So get the accent in the right spot. What is an arithmetic sequence? 2, 4, 6, 8. Who do we despise and hate? 5, 10, 15, 20. When are arithmetic sequences taught? They're taught in 1st and 2nd grade. What's it called? It's called skip counting. Okay. So if I look at that, that's what we do. So you're teaching an arithmetic sequence in algebra, and it sounds like, for a kid, they're going, holy crap, it's a sequence in which every term after the first is obtained by adding a common difference called D, and then you give me this damn formula? Are you trying to fail, kids? Okay, now, little kids learn to skip count by counting in multiples. Like I said, 10, 20, 30, 40, but we don't have to count in multiples. What we could do is count, give me a first number, and let's say I'm going to add 5s to it. So let me get back to my screen. So if I have a problem like 8 as my first number, I add 5, that gives me 13. I add 5, that gives me 18. I add 5, that gives me 23. And I say, I wonder what the next number is. And that's what they do in little kids' school. So the kids go 5 and 5, and they get 28 here. Isn't that neat? So if I had a problem like 2, and I decided to add 10, that would be 12, 22. And then what I could say is, what would be the next 3 numbers? And the kids would go 32, 42, 52. Pretty cool, huh? Now, what I could say is this. My common difference in this one is 5. So I take my first number, which is 8. I add 5 to get 13. I add 5 to get 18. I add 5 to get 23. And I add 5 to get to 28. So this was the 1, 2, 3, 4. This is the 5th term. So for me to find the 5th term of this sequence, which was the next term, how many times did I add 5? I added 5 4 times. Kind of interesting. Now, let's say I wanted to get to this term. That's the 1, 2, 3, 4, 5. That's the 6th term. So if I said, how many times did I add 10 to get to the 6th term? Let's see. I started off with the 2. I added 10. I added 10. I added 10. I added 10. And I added 10. 1, 2, 3, 4. I added 10 5 times. Now, I'm going to do one more, and then you can tell me what this is going to be. Let's say I start off with a number like 3, and I add 7. So that's 10, 17, 24. And I say to you, what is the 8th term of that sequence? Well, let's see. That's 4, 5, 6, 7, 8. So I'm adding 7. I'm adding 7. I'm adding 7. I'm adding 7 to get 31. I'm adding 7 to get 38. I'm adding 7 to get 45. 1, 2, 3, 4, 5, 6, 7. And I add 7 to get to 52. So the 8th term, how many times am I adding 7? I'm adding 7. I'm adding 7, turns out to be 7 times. Now, if we did enough of these, here's the pattern. That way, and again, I'm not giving you time to do this, but you'll notice if I'm looking for the 5th term, I'm adding the common difference 4 times. If I'm looking for the 6th term, I'm adding the common difference 5 times. If I'm looking for the 8th term, I'm adding the common difference 7 times. Oh my God, we see a pattern. So in terms of doing this, if I give you this sequence here, 4, and I'm going to add 8. So 4, 12, 20, 28. And I say to you, what is the 21st term of this sequence? Well, hopefully you're not going to draw a bunch of lines and do this. What you're going to do is you're going to look at this and say, my common difference is 8. And from this pattern over here, it looks like I'm going to add 8 one less time than the term I'm looking for. So I'm going to add 8 20 times. So I'm going to add 160. But what am I adding 160 to? The first term. So it's going to be 160 plus 4. On my 21st term will be 164. Now tell me, isn't this a blast? I mean, how easy does this crap get? All right, let's just do one more since you're having a good time. Let's say I have a problem like 3, and let's go ahead and add 11. So 14, 25, 36. And I ask you to find the 101st term. Are you going to draw out all those little lines and add your little brains out? Hell no, you're not, because you just saw a pattern. So what are you going to do? You're going to add 11. How many times? 100 times. So that's, just so you know, 1100. And what are you going to add that to? 3. You're going to add it to the first term. So it's the answer is 1103. Now, let's write that algebraically. If I ask you to find, let me rewrite this. You know, we just said we had this 3, 14, 25, 36. So here's what we did. We were adding the common difference 100 times. So the common here, let me say that again. We're adding the common difference, which was 11, and we're adding that one less time than the term I'm looking for. So 101 minus 1 times. So in doing that last problem, I'm adding the common difference one less time than the term I'm looking for, since I'm looking for the 101st term. And what am I adding that to? The first number. So this turned out to be 3 plus 100 times 11, which is 1103. Now, how do we write that? If I ask you for the nth term, I generalize that. So what I'm going to do is I'm going to take whatever my common difference is. I'm going to multiply that by one less term. So if I'm looking for the nth term, I'm going to multiply by n minus 1. So I'm looking for the 21st term. I'm going to multiply the common difference by 21 minus 1. And what am I going to add that to? The first term. Well, this is an arithmetic sequence. So let's use A for arithmetic. And let's say I'm looking for, this is the first term. So I'm going to use a subscript 1. So I have this formula. I'm going to take whatever the common difference is, multiply it by one less term I'm looking for. Why? Because I'm seeing that pattern. And what am I going to add that to? The first term. So now I have this beautiful formula that says, defined it as a sub 1 plus n minus 1 times d. And now I'm looking for the nth term. And whatever that term is, I'm just going to call that a sub n. So rather than dropping a formula on the board for the kids, you'd go through a bunch of these examples. I don't know what the hell I do with them. Well, what did I do with them? There they are. You'd go through some of the examples that I now can't find. Oh, there you are. And start to see a pattern that if you were looking for the 6th term, then you'd be adding the common difference 5 times. If you were looking for the 5th term, you'd be adding the common difference 4 times. So what we do is we generalize that and say, if I'm looking for the nth term of an arithmetic sequence, and that's why we call it A, that's going to be the first term plus n minus 1 times d. So if I say, let's say I gave you this sequence here, 12, 9, 6, 3, and I keep on going. So now I'm getting smaller. Okay. So what's my common difference here? Minus 3. So d is minus 3. So my formula is, let's say I'm looking for the, 31st term. If I'm looking for the 31st term, I have a sub 31 equals a sub 1 plus n minus 1 times d. So what is my a sub 1? That's the first term, which is 12, plus I'm looking for the 31st term. So it's going to be 31 minus 1, and the common difference is negative 3. So in terms of doing this, this is 12 plus 30 times a negative 3 is negative 90, and 12 minus 90 is negative 78. Okay, so my point is this. The formula is pretty easily derived once you see that pattern. And it's, whether D is a positive number or a negative number, whether it gets smaller or larger fractions, it doesn't matter. What we did is we saw a pattern develop and we developed some notation for that. Now, oftentimes, okay, let me stop there. I need to put my glasses on to see what the hell I'm doing here. Okay, it's 2:37. Mike, Mike, you're there. What time am I getting done?
2:40. You had 3 minutes.
Oh, crap. Okay, I'm done. I'm not going to go any further. Sorry about that. People, let me just say this to you. If you're looking for classes, go to the rpdp.net website. And I offer generally 1 or 2 workshops per week. And you get, depending, I guess, on your school district, you get units for that, CUs for that. If you go to my own website, which is hanlonmath.com, I have all kinds of resources. There are videos, there are chapters, and there are worksheets. The worksheets typically have a problem strategy or formula with a worked out example, and then with problem sets. And because I typically work with struggling students, I use nice numbers, as you should when you're introduced, particularly on initial instruction. Sorry, I didn't take any questions, but that's how I roll. Anyway, I thank you for attending. Appreciate it. That hour went too quick. Thanks.
Thank you very much, Bill. And we appreciate your wonderful presentation. I'm sure a lot of our participants appreciate your expertise and talent in this one.
Okay, just so you know, I'm full of it. All right, you guys have it. Thank you very much. I really do appreciate it.
Take care, Bill.
Thank you. Somebody just said I was brilliant. I thought I was just good looking.
So I'm posting the survey for this session. You may go ahead and click that link and send us your survey for your.
If you liked what I do, it's Bill Hanlon. If you didn't like what I do, it's Joan Ebert. Sorry, I couldn't cover more. Thank you very much, though, for that was a very, very, very quick session. I'd like to go a lot slower.
Yeah.
We love math. Yes, we do. We love math. How about you? Variables on the left, numbers on the right, stand up, sit down, fight, fight, fight. Okay, some of you don't know these chairs. I can tell just by looking at you. Good God. Tanya, do you know these chairs? Okay, start going to these workshops. You'll learn them, along with some lousy math jokes. Mike, do you need me to do anything or am I done?
Oh, you're done. You're done. Appreciate it.
My wife often tells me that. I'm done. Yeah, my website is hanlonmath.com. Everything on there is free. There's no usernames or passwords. Feel free to use that stuff. If you have a substitute, the videos would be nice because they're about 20 minutes long. They tell the kids what to write down, or write the title, the date, the objective. It goes through the definitions, identifications, how to say it, along with how, with the development of the procedures and then work problems. Thanks again. Okay, so Mike, do I leave this? How do I do it? Do I just leave the session?
Yeah, yeah.
Okay. Okay, you guys have a great afternoon. Take care now.
Take
Bye-bye.
care, Bill. So let's have a few moments for waiting for our next session.
Mike, the presenter was having a little bit of issue with the Zoom link, but I just sent him the correct one.
Okay.
So it'll just be a second. He's getting like an invalid notice or something.
Okay, thanks for fixing that.
Yeah, I'm just waiting for him to. Make sure he is on.
So while waiting for our presenter, you may click on the link for your attendance for the 6th and the last session for the room, but we still have, I think, a closing session, which there will be raffles. And if you want to win prizes, you might want to go into that closing.
Mike, I could not see the link to the attendance.
Oh, okay. Sorry. Let me do it again. Okay. Okay. I see some questions regarding credits, college credits. So there's an instruction on how to register through SUU. If you go to the hub, you should be able to, let me go to the link. You should be able to get that information. And so this is the link for the hub. And you should be able to go to information regarding registering for college credit.
Mike, can you double check the waiting room? Sorry.
Oh, sorry. Yeah. I just okay. So let me see.
Should we just say Algebra Zero, or should we include the missing step for success in the title?
You can just put Algebra Zero. We'll know which one.
Okay.
Yeah, it's fine.
Okay,
So I
Mike
see.
Rule.
Hi, Mike. Glad you
Hi.
made it. Sorry about that.
Oh, no problem. It's not my fault. Monica is on the way over here. So,
Oh, that's okay.
yeah.
So I'm gonna go ahead and leave the other Mike. He's the moderator for this room, and he can get you all set up with being the co-host and all that kind of stuff.
Okay, great. Really appreciate it. Hi,
Yeah, no
Mike.
problem. Thank you. Bye, everyone. Enjoy the session.
All right. Well, Monica's here down there.
Okay.
Hi, everyone.
Let me get you guys set up. Let me just it's a lot of quick changing. Let me just give me a second. Where's Monica? So, okay.
Are you going to be co-hosting with us in order for you to still allow people in the room? Because I'm now getting the alert to let somebody in.
Oh, yeah, I'll be co-hosting you guys, and I'll be admitting, well, you guys do your presentation, I'll be watching the room and admitting people.
Okay, thank you so much.
Okay, so welcome, guys. This last session for room 2 is about Algebra Zero, the missing step in math and algebra success. Our presenters are Monica Colbert. Monica Colbert is currently her 9th year as a middle school math teacher and a 3rd year as a math content coach in Montgomery County, Maryland. She has been a member of the instructional staff for Nevada Math and Technology Camp for more than 7 years. She has been, Monica earned a dual Bachelor's of Science degree in Mathematics and Secondary Education from Syracuse University and a Master's in Education degree in STEM Teacher Leadership from University of Maryland. Monica served as a AmeriCorps member with City Year Incorporated, where she provided math and English academic intervention in Washington, D.C. She is passionate about giving learners a fun and successful experience with math, especially algebra. And our other presenter is Dr. Michael Liu. Dr. Liu has worked over 27 years in education technology field in various roles. Michael Liu started his dissertation research work in 1988, applying artificial intelligence to design self-learning controllers for engineering process. This led naturally to his interest in human cognition. Since 1995, he has focused on developing K-12 mathematics supplemental material using education technology. His strength lies in the ability to coordinate between educators and programmers, turning the best practices into digital resources that can be shared by millions. One of Dr. Liu's passion is to reveal the inner workings of math and algebra and figure out the right way to engage students, which ultimately boosts their achievement. By helping students one by one, he believes we can transform math or algebra from STEM keeper to gateway. Ladies and gentlemen, please welcome Dr. Liu and Monica Colbert.
Thank
Thank
you.
you so much.
Take it away, guys.
All righty, I am going to share my screen. Okay, are you all seeing? Can you tell me what it is that you might be seeing?
Just a black screen right now.
Okay. Let's see here. Where might my controls be? Okay, are you seeing the
Oh,
screen?
yeah. No,
Yes.
Okay, yes?
Yes.
Okay, wonderful. All righty. So we are here to share with you about Algebra Zero. And as you heard from Mike, and thank you so much for the warm introduction, we are going to focus on the missing step in math and algebra success. I am Monica Covert, and I'm so happy to be here with you all. So who this session is for, and hopefully who can benefit from this, really educators of grades 3 through 11, and especially administrators. And we all are in the right room, right session, so thank you again. So the main goal of Algebra Zero is to double student achievement in math with half of the time. And with that, we hope to have students relearn once to retain forever. Oftentimes, I know having students retain the math understanding is something that I feel has been my greatest struggle, because I still always find myself having to revisit concepts, revisit skills. So through Algebra Zero, which we're excited to share with you, you'll hopefully see some new ways in which we can mitigate that. So the top 3 challenges for teaching and learning, which was shared and highlighted in this report, that honestly is so relevant in today's classrooms and something at which we can see regardless of where we are in the nation, is that there's a lack of motivation amongst learners. And this gives teachers oftentimes a greater challenge, a greater workload, just to try to reignite student interest in learning math. And we are finding, the reports have shown, that students are usually coming to the on-grade level math courses unprepared. And with this unpreparedness, there are several gaps that teachers are having to fill in. And while that's expected, because students are in various places and they are entering just with different skill sets that they bring to the classroom, the unpreparedness usually is why teachers are struggling with getting all students to achieve the common goal, whether it is algebra or whether it's a lower math. Unpreparedness is the greatest challenge. And that relates to how there is such a wide array of learner needs. Oftentimes, teachers can't pinpoint the way to get to every student, and it's time consuming just for us to reach each and every student to fit their exact needs and exact learner styles. So with these 3 challenges, we're hoping that something different can support learners, can support teaching as well. So the traditional teaching method, which I can attest to, which I gained from my methods courses in undergrad and just throughout my years of experience, typically we deliver the conceptual information by showing students the procedural way of addressing problems. And oftentimes it is the concepts are secondary, but the procedure is typically leading the instruction. And so the emphasis oftentimes is placed on the process and practice. And usually students are just trying to memorize, what are the next steps? How do I do this? And trying to recall exactly what they saw the teacher model. And from there, pretty much repeating what has been modeled to them, and that mainly being a process. So where we think there could be some innovative way of teaching learners, especially specifically for algebra, we find that it's most important to do what will allow for a teachable moment. And what can generate a teachable moment just really means like allowing students to be a part of that teachable moment and not just have teaching being something that is brought to them. We also find that it's so important to focus on conceptual understanding. And while I had just mentioned the concept is usually paired with the procedures, conceptual understanding is how learners are guaranteed to really retain the information, really retain the content, and through that further apply it, as opposed to just the process of how to do something step by step. So with that, it will automatically promote computational fluency if students understand the process, understand the concept and then apply that. And of course, practice has to be a part of anything that we do. So computational fluency is guaranteed to come after we've engaged them, after they've mastered the conceptual understanding, and then can practice their way through. So one way in which we think that this is going to change, I'd say, the teaching game, so to speak, is through narrative-based approaches. So narrative-based approach is literally a narrative around math. And by that, we're really meaning fictional stories, not word problems like we usually think of when students are pairing literature and mathematics, but actual stories and a story-based approach in order for students to read a story or hear a story, maybe even watch the story. And through that, they're learning conceptual understandings that they then are applying. So the storyline that Algebra Zero has developed, and all of which I'm hoping you all will one day explore and use in the classrooms and in your schools, it reaches from grades K all the way through. And each grade band, the stories cover in its chapter stories, so it's like a series, and it covers every math concept, every math standard, depending on which grade band you focus in on. I'm a middle school math teacher, so what I've loved best has been the middle school story, and that one is best for the algebra students, beginner algebra students. And while I say beginner, it could also be for students who are reviewing algebra and just trying to make sure that they build their algebraic thinking and can have the conceptual strength in order to use that moving forward. So focusing in on that, here's actually one of the 3 series that's been developed so far with Algebra Zero. And this goes into variables, it touches on integer operations, algebraic expressions, linear equations, and so on. So you can just kind of take a look at it. And this is just one example of how we've engaged students in conceptual understanding and having them watch stories and watch videos that make math conversational, but also have them understand what really is this math and what does it really mean and how can I best understand it. This has been quite an amazing experience when I had the opportunity to use this in Nevada as I was at University of Nevada, Reno with a group of students for a summer program, and it hooked them. We have come into an age where binge watching is so common and students love a story. They love something that can get them to say, well, what happens next? And this narrative approach to teaching algebra specifically, it really allows them to just enjoy the learning, and it doesn't necessarily feel like someone is just directly teaching them through direct instruction and showing them processes and procedures. So this has been something that I can say has completely enhanced my teaching experience, especially in the sake of integer operations, which you're going to hear Mike speak on. And that's something that I can say that's an area that I saw the greatest improvement. So specifically thinking about operations and integer operations to be exact, there's usually this emphasis on the different ways in which we can add integers together. And so as we consider, let's say 2 + 3, there's different ways if we include integers, there's different ways that we can say what exactly we are adding together. So we can add positive and negative, negative and negative, positive and positive. So with this integer operations, typically students are learning this by way of rules, and those rules oftentimes have to be memorized. So if I am teaching students and they're adding a positive and a negative, and they're having to think about which one is greater or which one is less, and then considering a number line, usually it does involve some kind of rule memorization. And while that serves some students, I can't say that it's for everybody. And I'm sure if you are one that has experience teaching integer operations, you probably have experience where students oftentimes can't hold on to which rule to use and where and when. So there's been a shift in that as I've used this story-based approach in order for students to see it a different way. And so the subset of learners that this fits, it works for them, and they can catch the rules and they can apply the rules, and that's fine. And it's for some, but it just has not been for everybody. So as we consider integer operations, and specifically the addition of integers, there's so many different ways that we can go about adding two values together, two quantities, and having this be shown just with the values, or with the, I've used like a positive and negative symbol before and just had students see what might pair up or cancel out. There's so many ways that we can do it. And it's oftentimes just the hope that we're going to gain understanding, and the students are going to gain understanding by ongoing practice. And this ongoing practice, I can't say it always allows the concept to sink in about exactly what is it that we're sharing with them, and how is it that they can actually retain the conceptual understanding. So if I could say a connection with the Albert Einstein, what we know insanity is doing the same thing over and over again and expecting different results. Well, not to throw any shame, because I'm still a middle school math teacher. So I'm in a classroom and I have some things about my practices that relates to what I just touched on. But honestly, doing the same practice over and over again and expecting math success, that in a way has caused a bit of insanity or a disconnect between the classroom practices and student outcomes. So if there is a way to show students the conceptual understandings in order for them to learn it or relearn it right away one time, and then really retain it, hold on to that and apply it, we'll see so much more success with students. So I'm gonna allow Mike to hop in, and Mike will share with us some ways in which Algebra Zero has arrived at giving students stronger conceptual understandings right away.
All right, thank you, Monica.
Yeah, do you want me to keep this up, or would you rather share?
Well, can I share my screen, or?
Of course.
Let me know when you see my screen.
Okay, have you started sharing?
I thought I did. Well, give me 1 second. Let me share again.
And I'll stop my share.
Okay. Can you see mine now?
Yes, we can.
All right. Give me 1 second. Now, let me review a little bit, what Monica said. I know a lot of those content are pretty boring to kids. I don't blame them. Let's say out of 100%, maybe 20% of the kids are, like mathematics, and we can't deny the fact the majority somehow, just something they have to finish, and they're not really crazy about it. And just an integer operation, the for operation alone, for addition, we have 4 different rules. Okay, then subtraction, we introduce 1 rule. We say, wow, great, there's only 1. But however, if you really look at it, what the rule says is that subtracting a number is the same as adding is the opposite. Even though it's a 1 rule, but to a lot of kids, that's at least 2 rules. Why? Because we're talking about either subtracting a positive number or subtracting a negative number. Anyway, so just gave you one specific example. A little like a simple, subtraction problem, what we deal with, in grade 1, grade 2, like a 5 minus 2. Now it becomes 5 plus negative 2. He says, that's crazy. What are you guys doing? Why we're doing this thing? Now I don't even know how to subtract anymore. Before it's 5 subtracted 2 equals 3. Everybody knows that. But now based on the rule, we hardly explain why we're doing what we're doing. Again, back to the multiplication, there's another 4 rules, basically it's the same sign versus the opposite sign. You know, some people say, hey, the 4 rule, we can cut it down and, you know, change that into 2 rules to make it, you know, kind of like a little easier to memorize, but there are still 4 rules because the same sign. What do you mean by that? And eventually you have to explain to the kids, positive, positive, that's the same sign, negative, negative, that's the same sign. Then, I mean, all of those things. But anyway, I'm not trying to make you memorize all the rules. The goal over here to help you see how much actually we want the kids to memorize it. It is crazy. And, barely 10 years ago, I was a programmer. Programming really, the course is really for college. Now we push down to high school. I'm not saying we shouldn't be doing that. I'm not saying that, there's a place for all of those courses. But what I'm trying to say is that we want kids to learn more and more. And now with the, the pandemic, the unfinished learning, there's just so much we need to catch up. So the traditional way need to be improved a little bit. Again, I'm not trying to say traditional way is bad. No, actually, traditional way is a very, very efficient when it works. That means, for the 20% of the kids, I just pick a number, 20%, it could be 40%, could be 50%, but for the 20% of the kids who just get it, traditional way is the best way. You tell them what to do, they can produce the correct answer. What's wrong with that? Nothing wrong with that. Well, we can discuss more, but we don't have time today. But anyway, for those kids, traditional way is the best. But what about the remaining 80%? They just can't memorize all those rules anymore. Up to a point, some kids, they were pretty good at elementary school level, moving to, middle school. And some have a problem, some don't. Then some are moving to high school, they start having a problem. But anyway, when we use the traditional way, and at certain point, and kids just are overwhelmed by all of those things, they have to memorize it. So now the question is there a better way? Is there a better way to do it? So let me go back to the same problem, Monica used earlier. So this part I will call surface manipulation. And the bottom part, I don't have anything right now, is called inner working. To explain what I mean by surface manipulation and inner working, I'm going to use one specific example, like the light switch. Everybody knows the light switch. Everyone knows how to use it. So if you really look at it, this part, I will call it surface manipulation. Switch on, off, that's it. The internal thing, normally we don't really show, that's the inner working. For simple task like this, just switch the lights on and off, you don't need to explain a lot of inner working. I mean, it's getting in the way. This is one thing we need to do, just to turn it on, turn it off. So you just learn the surface manipulation, that should be it. However, when you deal with mathematics, when one thing is built upon another, there's hundreds and thousands of procedures and concepts, we need to understand. Without inner working for even the most fundamental one, it won't last. So some, just after a while, everybody feel overwhelmed. Now let's go back to this addition problem. So what's the inner working? Well, what I show over here is a traditional tally mark. That's a 1, that's a 2, that's a 3, 4, 5, tally mark. Very few people have a problem with the tally mark. But the problem over here is that when we deal with integer is there's no way to represent the positive and negative. Okay, there's no way to represent that. So what do? What we do is we modify it, improve the traditional tally mark. How do we do that? Well, that was a 2D. Now I introduce a raised raised tally mark to represent positive 2. Then I, introduce recessed tally mark to represent negative. So what's addition? Addition means, you put all of them together. So think about it. You have 2 bars. You have 3 slots. When you put them together, they're supposed to be exactly the same size, just because, one over here and one over there represent the same size, at the absolute value. But that's another thing, we can discuss in the near future. But anyway, when you put them together, what do you see? What's going to happen? 2 bars going to fill the 2 slots. So you have 1 slot left. So what's 1 slot? That's a -1. So if you just have a couple examples to cover, like +5 plus, -3, or +1 or -1 plus, pretty soon, just actually, just a 4 or 5 example down the road, the kids can see the pattern. Okay, so let me switch over to the demo side and show you a little bit. Can you see my new screen now? All right. Now, computer automatically generate the problem. And here's the inner working. You can also call it explanation. So basically, that's a +5. That's a -1. What's going to happen when you put them together? Well, you cancel 1 pair. So you have a what? 4 bars left, 4 raised tally mark left. So that's a +4. So what about this one? Well, what do you think that's going to happen? So you just actually watch it a couple more times, and most of the kids actually get it. And remember, we said there's 4 rules for integer addition. And now they don't even need the 4 rule anymore, at least for addition up to this point. And this is kind of like a demonstration. Then we have a kind of like a practice. Basically, the kids can just drag and drop. The funny thing is, once kids understand the inner working, one kid even says, +1. Yeah, that's what you guys want me to do. But you know what? Can I do this? I have 2 bars and 1 slot. They're supposed to be +1. Well, we acknowledge, says that, yeah, you're correct. That's why we modified the program to make it work. Kids can see, yeah, that's a +1. So here, +2, you do that. So that's kind of like a digital hands-on or digital manipulated. And now, once you see that, so yeah, well, by default, you can use a +1 or a +3 or just, 3 by default. Anyway, we don't have time, so that's why I'm not going to show the rest. Basically, the entire content, entire, thing are free for the whole state of Nevada. So I'm going to go back to, let me see. Now, instead of memorizing 4 rules for addition, like I say, when you have an integer, positive, the kids can see, well, when I have a, 2 bars and 3 bars, of course, that's how I'm gonna add. Or when I have a, raised, tally mark or recess, this is what's gonna happen. When I have a recess or the slots, and you see, just simply based on that modeling, kids can form a mental image. So they can come out with the rule on their own. So basically, all of those rules we're trying to teach should be learner's own conclusion. It should be something, you know, they arrive at after they understand the content and concept. They shouldn't be the material we use to teach them. So all of those textbook material, I mean, the majority, if we do it this way, they don't need to memorize, you know, they will automatically, let's put it that way. They do need to memorize it, but they will automatically memorize those things. It's a better way. But like I say, you know, I'm not saying, you know, we shouldn't, you know, use the traditional way. Like I say, you know, for a percentage of the student, you know, kids, that's the best way to teach them. But for the remaining kids who just cannot do it with the traditional way, this is another way. Again, I'm not saying this is the best way, this is the only way. This is just a one additional way we find, you know, very effective to teach, you know, those students. All right. So should I give it back to you, Monica?
You can keep it going.
Oh.
Yep, thank you. All righty, so thank you so much, Mike. That was well explained and said. So truly, as we have seen, and I appreciate someone noting that that was similar to the zero pairs, just a different way of showing it. And there's actually interactives within the site where you can see the zero pairs shown for the concept to really be understood and owned by the students. So through Algebra Zero, we have found the outcomes to be, and we're really confident those that are looking forward to using it in the near future, we are certain that you'll have an improvement of student engagement. The interactives plus the stories, it just gives students a new way to see the math and to understand the math. And through that, it reshapes their attitudes about math learning and builds their confidence. And I can honestly say that this is something that doesn't just relate to the students. There are several teachers, and I'm a math content coach. So oftentimes someone can love math, they can be amazing at teaching it, but there are sometimes areas where the concept is not fully understood by the teacher, although they can teach it very well, and although they can deliver the instruction to allow students to understand it and go through the process of whatever it is that that math topic calls for. But typically with a teacher learning the conceptual understanding in a new way than it was originally taught to them, it even builds their confidence. And it can ultimately reshape the tone of the class for students to be engaged in something that is exciting. And they can then adopt the conversation that they hear in the stories that allows them to lead through their own understanding, where they're able to, like Mike said, develop the rules themselves and not just have it shared with them, memorized, and then applied. So these three areas, I have personally seen the proof of this outcome as I was going through Algebra Zero with some of the students in Nevada, and the interactive specifically allowed for my students here in Maryland to really grasp it quickly. And it took a lot of the load off of me because I did less front loading and more just discovery based. We can go to the next one. So it's truly guaranteed to double the achievement with half of the time. So as I mentioned, just having them discover what it is that these concepts entail, it gives them an automatic way to own what it is that they're learning. And with that, a lot less time is spent trying to get students to memorize something or trying to get students to show that they have it by giving them different types of problems where the rule application might fall short for some. So relearning, and it could be a first time learning, but relearning one time through the proper way of showing the conceptual understanding, it does produce retention forever. So as we consider this approach, if you can go to the next one, it's going to support teachers' well-being by allowing teachers to work smarter and not harder. I can say it's a lot of the load placed on teachers' hands when they are the ones just trying to share their understanding with students, as opposed to students gaining that understanding on their own through what is facilitated by the teachers. So if the students have an opportunity to see something, hear it talked about, see the interactives, and have the interactives either being demonstrated with them or they can actually be hands-on with it, we see a lot of opportunity for students to perform better, to feel better about the math that they're learning, and to enjoy it in order for them to be confident, in order for them to have a different attitude, and for teachers to feel like it is less teacher-led and more student-centered and student-led through the discovery of the concepts that they gain from the stories and the interactives. So Algebra Zero, as Mike had stated in the chat, it's readily available, well, gradually going to be fully released, but there are parts of it that are actually available to you all even today. And there are approved PD credits through Nevada's Department of Education. So you all can have a way in which you can get PD and get credit for it by learning ways of using Algebra Zero, learning ways to apply it in the schools, or have your cohorts, your teaching cohorts, consider it in ways that the students can just have this, I don't want to say more so an intervention, but it's a very strong supplement to any curriculum. It's not going to replace anything, but it absolutely is guaranteed to give students a new way of seeing the math and exploring the math. So you can contact Algebra Zero through this email, and you should absolutely stay tuned to what's ahead, as the entire state will have access to this. And it's such an innovative way of exploring math and just enjoying it. I know I enjoy watching a good story, and I guarantee you and your students will also. So I think we could show you all a little bit of the stories, if you're okay with that. And I'm excited that some of you were eager to have a look before we even finished up. So if you all are okay with it, Mike, are we able to share any of the story for them to see the algebra clip?
Sure. Yeah, and in the real story, we do have a rigorous content. Like I say, for algebra part, it goes from a variable, algebraic expression, linear equation, function, it touch every one of them, and actually covers that, in a pretty, a deep, step. But the thing is, for today, we really don't have a time. So what I can do is just show you the story part. Let me see. Should we play from the first one, just a couple minutes? And
if that's okay, I believe that'll give them.
Amelie's Algebra Journey, Episode 1, The Incomplete Message. Topic covered, Overview of Algebra. The first episode not only introduces the characters and setting of the series, but also explains why algebra is needed at all in everyday life. Our story begins in the Port Kingdom, where Amelie, our protagonist, lives alone with her father, Mr. Wells, a bookkeeper and auditor to the king. She often meets with her father on his way home from work, which gives them time to talk about each other's days. This time, however, Mr. Wells bears unpleasant news. He has to leave the very next morning to travel to the neighboring kingdom of Sal for an emergency audit of their trade office. Seeing her concern about this troublesome trip, Mr. Wells tries to change the topic by asking Amelie about her schoolwork. Relieved at this diversion, she expresses her frustration with translating word problems into equations. Her father tries to help by comparing the process of solving a word problem to extracting salt from the earth, since salt production is a significant part of the local economy. In the same way that the extraction process rids salt of impurities, algebra helps eliminate unwanted verbal descriptions in word problems. This demonstrates one small aspect of what algebra can do. Mr. Wells then compares algebraic processes to patterns in the English language to translate daunting, unfamiliar concepts into familiar terms both Amelie and most student readers can process with ease, thus building confidence. The story ends on a cliffhanger. Amelie's father goes missing while away in the Sal Kingdom, and Amelie receives a message with only a few legible words that suggest that something bad has happened to Mr. Wells.
Monica, is the sound okay, or?
Yes, it's been great.
Oh, okay, great. So the first episode actually is kind of like an introduction to the whole story. And basically for algebra, it's kind of like explain a little bit, why we need algebra. It's kind of like why we need this language, why other languages are not good enough in certain cases. So that's basically introduction. So next episode is all about, variable. Again, in a traditional way, when we teach variable, normally we just tell the kids, hey, variable is a letter or a symbol we use to substitute, a number in our calculation. And again, that's a conclusion. That's a conclusion students should arrive at after they understand it. So when we just simply feed that conclusion to them, it's not long lasting. And they have no idea. Some of the kids even say, I thought, letter belong in English, we should use a number in math. I don't understand. I even have a hard time to calculate the regular number. So now you give me a letter. How do I calculate with a letter? They really have no background to understand why we have to use a letter or a special symbol to in our computation. So the second actually episode, go through the story and by, building the right concrete, context, kids can see, students can see, wow, this is why we need the variable. Again, in the brief introduction, you don't really see that part, but in the real story that's 15 minutes long. And once they watch that, they understand exactly why we had to use a variable or why we have to introduce this new
Episode number
concept.
2, the magic crystal ball. Topic covered? Variables. Amelie has been staying with her aunt while her father is away and is troubled at night by a disturbing dream. In the dream, a mysterious woman appears and says she can help Amelie with her quest to find her father. However, the woman needs to test Amelie to be sure she is mentally ready for the challenges ahead. Otherwise, knowing the truth will put Amelie in great danger. The test consists of what appears to be a magic process whereby the mysterious woman can read Amelie's mind. To avoid the ambiguity and complexity frequently associated with describing creatures or objects with words, the woman proposes that they use numbers. Once Amelie picks a random whole number, the old woman's crystal ball can predict which number Amelie is thinking of. It is puzzling at first, but based on a few clues provided, Amelie realizes that using variables can help reveal how the magic actually works. When she wakes up the next morning, Amelie realizes she must see the king herself. She vows to go to the royal ball where the king has promised to greet everyone there. But no one can attend without an invitation, and it won't be easy to get one.
Okay, today we use a specific example, integer operation to show you actually there's a way to speed up the learning. Actually, there's a way. And it is a very, very likely, if we present it right, and kids can compare, think about it, before some kids, they take algebra 1, then, they fail it. And then next year they have to take it, it's not uncommon even for some of the kids to take it 3 times. So compare with that. And that, what we're saying is, we can double the achievement with half the time. We're not saying actually, instead of a year-long course in Algebra 1, we can really cut it down to a half year, even though for that 20% of the kids, I do believe is very, very possible. But for other kids who had to take it, twice or 3 times, so if we can just teach it once like this and be done with it, and that's what we're saying, that's how we double the achievement, with half of the time. So,
Mike, is it okay for us to answer some of the questions in the chat?
Oh, sure. Sorry, I didn't
Okay.
have a time to look at the chat. Sure.
It's okay. It's okay. So if you wouldn't mind maybe just putting up the last slide, and then I can get started with addressing some of the questions in the chat. And thank you all
Sure.
so much for asking such good questions. So the first thing I see is, when will we get full access? So the access should be fully rolled out by mid 2023. Is that accurate to say,
No,
Mike?
actually, that's the part I can talk about it.
Okay.
And even though it's a free, to be honest, it's so hard to get the words out there. It takes so much time, even so much, effort to really make everybody aware. So it's available now. And basically it's available now. It's really a matter of, so email us, info@algebrazero.com. We can give you the access. I happen to see, another message says, I think this is something probably everybody, cares. How would you recommend, we use Algebra Zero? It's a very, very hard to change your curriculum. We're not trying to change your curriculum. And the thing is, you can keep your curriculum. Nothing wrong with that, except the introduction part. Every teacher actually is struggling on a daily basis, try to engage the kids. They have a solid material. I'm not trying to say the traditional material are bad. Okay, no. It's lacking certain things. One of the component is lacking is the engagement piece, and to a degree, is a conceptual understanding. So let's say, based on your pacing guide, based on your curriculum now, next week, I'm going to teach a variable. So you use Algebra Zero as an introduction. Show, the kids 15 minutes, that story, then discuss it. They build a, kind of like a background, why we need to introduce this a new concept. Then you can just keep using your existing material. Nothing wrong with that. Use the experiment until you get into algebraic expression. So then, you use Algebra Zero to introduce that part. That might be another week or 2 weeks long, course, but just use this thing for 15 minutes, discuss it for 15 minutes and half an hour, be done with it. That's it. Then, by the time you need to introduce linear algebra, linear equation, again, use Algebra Zero. So I think that's kind of like the easiest way to incorporate Algebra Zero into your existing curriculum, because a lot of teachers don't really have any good introductional material. So use this, and that's the easiest way. Another way is, summer is coming. Think about it, summer coming. Well, because unfinished learning or learning loss, whatever you call it, we all have to do something during the summer. But we all know a lot of kids, even maybe some teacher to a degree, says, I just finished Algebra 1. So what should I do? I've been teaching it for 10 months. Now you ask me to recover everything in 2 weeks, repeat the same thing. So in that case, things you're looking for something new, use Algebra Zero. So that's another way to improve it. The third way is there's really no more change. You keep doing whatever you've been doing. However, just tell the kids, says, hey, next week, we're going to introduce, let's say, system of linear equation. Here's a story. Here's a website. Go back and, watch the story, read the story on your own. It's very hard to get the kids motivated the very first time, but based on our experience, once they watch it once, a lot of kids want to go back. So that means, there's really no additional work on your part, except, reminding them, here's a website, go back. Also, what we're trying to do is implement SSO, when the kids and teacher, log into your existing, management system, there's going to be an icon on the desktop. All they need to do is click on the icon. That should be it. So there's so many ways, we can implement it without interrupting your existing plan, existing everything. So that's how I would recommend, until someday you feel like, Mike, we should really work together and come out with a brand new curriculum for our district. Well, that's another story, maybe a couple of years down the road. But, we're flexible. Our job is to make your life easier by providing those things. Now, one more task for you. I'm sorry, Monica, you can say something.
It's okay. Would you be able to show the last slide so that they can get the email address? And there's such good questions. I want to make sure that we get to as many of them as possible. The videos are, I'd say, between 12 to 18 minutes. And as Mike stated, they're really a great way to introduce the concept. Someone had asked whether, what's the difference between these videos and the ones that come directly in your curriculum? This is story-based. So students will be able to recall what happened in the last episode, and therefore it just gets them all engaged in like, well, what's going to happen next? Because it is not just focusing on the math. It is actually a story, and it's this narrative that they're already hooked and they want to know what's going to take place in the upcoming episodes. So it's a way to just bring the students together. It builds and strengthens the class community. And through that, they're guaranteed to learn something that will stick with them for them to apply it. The recommendation in terms of like how long, well, there's 8 episodes in the algebra series, and I'd say each one is about 8 episodes. Is that safe to say for K through 2 and 3 through 5?
Yeah, for algebra, the story 8 episode, and actually we have an entire, curriculum for even, Algebra 0 to Algebra 1, and basically, if you only have a limited time, use this episode. If you have more time, talk to us. We have a lot more material.
Right. It's so much
I can't
more.
even present today. Again, another thing is, let's say, for your 3rd grade, third through 5th or 3rd through 6th, school. And if we implement it, right after you get back, after Christmas, New Year, then, and, the smarter balance testing is coming maybe in March or April. And you might think I exaggerate a little bit. I would say, for some school that are really serious about it, if we implement this thing, well, I think, you can see a big difference by the time, testing is here. Because for 3rd grade, we have actually 3rd grade, we have a 10 episode. We cover, the geometry shape and, the concept of, parameter area, they only touch a little bit. Then, the, addition, subtraction up to like 1,000. Then the fraction, basically, you have to, actually the major component over there is the unit fraction. So unit fraction, then, so 10 episode covers all the major concept over there. Like I say, 3rd grade, the reason I mentioned 3rd grade is because 10 episode, and basically literally 2 weeks or 3 weeks. If you gave us a month, we use a story, kids actually can really improve their conceptual understanding, followed by the practice, and that'll make the practice a lot more effective. So for 3rd grade, I think literally a couple months, 2-3 months, you can see a difference. 4th grade, long time, to be honest, you have to go back to the 3rd grade. Even some of the kids who can answer the 3rd grade material without any problem, but do they really understand what you mean by unit fraction? So it's better to start from the 3rd grade, then build up to the 4th grade. That's why the 5th grade, the higher grade, it takes a little more time. That's why even though we have a material to cover the entire basic K through 10, I would recommend all the kids should read the story on their own. But to really make a difference, let's work on the 3rd and 4th grade for the elementary school level. Literally 2 months. If we're serious about it, we can see a big difference.
We have 2 minutes left, and I want to make sure
sorry.
that we address a couple things about the current languages that it's offered in and ones that they can expect to come, as well as the connection between Clever, if student logins would be something that Algebra Zero and Nevada are going to incorporate.
Yeah, we cut the also another thing. I'm sorry, Mike. is there any way we can save the chat? Because I didn't have a time to,
We can save it by just, you can
Oh.
press the 3 dots and then select
okay.
save chat.
I want to make sure we save that because the question we never had a,
If we could just say for anyone that is eager to make use of this before their school fully adopts it, do email.
yeah,
info
email
at
me,
algebra-
info
yeah.
at algebra0.com. We have actually a group of people monitoring that email. We'll get back to you right away.
All transcript and recording will be posted in the future.
Okay,
But
great.
yes, all of this transcript in the chat and transcript of the presentation will be incorporated to your Canvas hub. So
Okay, great.
just watch for it in the future.
All
Thank
right.
you, thank you.
Is there a survey to complete? You gave us the attendance. Is there a survey?
I think that was the survey link that Mike placed in the chat.
What, just the attendance?
It's a
Oh,
Google
there it is.
form.
There it is. There we go.
So
All right, appreciate that survey.
I put a bunch of links. One is for the attendance, one is for survey, and one is for the link for the closing. We have a 15 minutes for the closing, and there would be a raffle on the closing if you want to win the prize. I believe there are big prizes on the very end. So log on to that session, closing session, and for you guys to win big prizes.
Thank you all so much.
So I'd like to thank I would like this opportunity to thank Mike and Monica for sharing with us Algebra Zero. If there are questions, you can email Janie Maloney and the team, and we will connect you with the presenters, and all your questions will be answered in a later date.
Yeah.
So the
thank you all for coming.
will be able to answer those questions.
Oh, I'm excited for you, Jennifer. I'm hoping that you'll be able to use it and enjoy it. So we're looking forward to everyone using it widespread. Thank you all so much. And thank you, Mike. Well, both Mikes.
Thank you, Monica.
Take care, everyone.
Thanks for coming, and see you at the closing.
Thank you, Mike. Really appreciate everything.
Yeah, same here. I appreciate your presentation. We enjoy it.
Thanks.